Welcome everyone. Today, we'll explore the fundamentals of structural materials used in construction and engineering. These materials form the backbone of our infrastructure and industrial systems, so understanding their properties and performance is essential for engineers and inspectors. Structural materials are those designed to bear loads and maintain integrity under service conditions. We'll also discuss the critical relationship between structure, processing, properties, and performance, which governs material behavior. Structural materials are those specifically designed and selected to bear loads, resist deformation, and maintain integrity under various service conditions. They form the backbone of engineering structures such as bridges, pipelines, aircraft, and industrial machinery. The performance of these materials depends on multiple factors, including environmental conditions like temperature and corrosion, the type of loading such as tension, compression, or fatigue, and the duration of exposure. Key attributes that define structural materials include strength, which is the ability to resist failure under applied loads, stiffness, which measures resistance to elastic deformation, and toughness, which indicates the capacity to absorb energy and resist crack propagation. Other critical considerations include density, which affects weight and is vital for aerospace and automotive applications, durability, which relates to resistance against corrosion, wear, and environmental degradation, and manufacturability and cost, which influence economic feasibility. From an inspection perspective, structural materials require strict adherence to specifications and traceability to ensure compliance with standards. Inspectors must look for defects such as cracks, voids, inclusions, and delamination, as well as degradation mechanisms like corrosion and creep that can compromise long-term performance. Understanding these fundamentals is essential for engineers and inspectors to make informed decisions about material selection, maintenance, and failure analysis. The behavior and performance of structural materials are governed by an interconnected framework often described as the structure, processing, properties, performance relationship. Structure refers to the arrangement of atoms, molecules, or grains within a material, including bonding type, crystal lattice, phases, and defects such as dislocations and pores. Processing encompasses the manufacturing routes that define this structure, such as casting, forging, rolling, heat treatment, sintering, molding, and curing. Properties are the measurable responses of the material to external stimuli, including mechanical, thermal, electrical, and chemical characteristics. Performance is the ultimate measure of how well the material fulfills its intended function under service conditions. Considering factors like strength-to-weight ratio, fatigue life, and corrosion resistance. For example, in metals, heat treatment can alter phase composition and dislocation density, significantly changing hardness and toughness. Ceramics rely on sintering to reduce porosity and enhance strength, while polymers achieve desired thermal stability through curing and cross-linking. Composites derive their properties from fiber orientation and matrix quality, which are controlled during layup and curing. This systemic view emphasizes that material selection and inspection must account for processing history, as it directly influences microstructure and, consequently, performance. Materials are classified into metals, ceramics, polymers, and composites. Each class has unique bonding types and properties that influence their applications. Structural materials are broadly classified into four major families: metals, ceramics, polymers, and composites. Metals are crystalline solids characterized by metallic bonding, which provides ductility and high electrical and thermal conductivity. They are further divided into ferrous, iron-based, and non-ferrous categories. Ceramics include crystalline oxides, carbides, nitrides, glasses, and cements, bonded ionically or covalently, resulting in high hardness and temperature resistance but low toughness. Polymers consist of long-chain organic molecules and are categorized into thermoplastics, which can be remelted, thermosets, which form irreversible cross-linked networks, and elastomers, which exhibit rubber-like elasticity. Composites combine two or more distinct phases, typically a matrix and reinforcement, to achieve tailored properties such as high strength-to-weight ratios and improved damage tolerance. Bonding plays a fundamental role in determining properties, metallic bonding allows dislocation motion, enabling ductility. Ionic and covalent bonds confer hardness and high melting points but limit plasticity. Secondary bonds like van der Waals forces govern polymer flexibility and viscoelastic behavior. Understanding these classifications and bonding mechanisms is crucial for predicting material behavior and selecting appropriate candidates for specific applications. Metals are widely used due to their strength and versatility. Let's look at their structure and properties, and the distinction between ferrous and non-ferrous metals. Metals are characterized by crystalline microstructures composed of grains with specific lattice arrangements such as face-centered cubic or FCC, body-centered cubic or BCC, and hexagonal close-packed or HCP. These structures influence mechanical properties like ductility, toughness, and strength. Metallic bonding allows dislocation movement, which imparts ductility and enables plastic deformation. Metals exhibit high electrical and thermal conductivity, making them suitable for structural and functional applications. Their properties can be extensively modified through alloying and heat treatment processes. For instance, quenching and tempering in steels adjust hardness and toughness, while solution treatment and aging in aluminum alloys enhance strength. Common processing methods include casting, forging, rolling, machining, and welding, each affecting grain size and phase distribution. Metals are widely used in pipelines, pressure vessels, structural frameworks, turbines, and electrical components. Inspection of metals focuses on weld integrity, heat treatment verification, and detection of defects such as cracks, inclusions, and porosity, which can compromise performance under load. Ferrous metals, primarily iron-based alloys, include carbon steels, low alloy and high alloy steels, stainless steels, and cast irons. They dominate structural applications due to their cost-effectiveness, versatility, and wide property range achieved through alloying and heat treatment. Stainless steels offer corrosion resistance through chromium additions, while cast irons provide excellent damping and castability. Non-ferrous metals encompass aluminum and its alloys, copper alloys, nickel-based superalloys, titanium, and magnesium. These materials are selected for specific attributes such as lightweight for aluminum, high conductivity for copper, high temperature strength for nickel alloys, and exceptional strength-to-weight ratio for titanium. Selection criteria often involve balancing strength, corrosion resistance, temperature capability, cost, and availability. Applications range from aerospace components and marine structures to high-temperature turbine blades and chemical processing equipment. Understanding these distinctions is essential for engineers to optimize material performance in diverse environments. Ceramics are known for hardness and temperature resistance but are brittle. We'll examine their structure, characteristics, and limitations. Ceramics are inorganic, non-metallic materials bonded ionically or covalently, resulting in exceptional hardness, high stiffness, and outstanding temperature resistance. They include crystalline oxides, carbides, nitrides, glasses, and cements. While ceramics excel in wear resistance and chemical stability, they are inherently brittle due to limited plastic deformation, making fracture toughness a critical design consideration. Processing typically involves powder synthesis, forming methods such as pressing or slip casting, and sintering to achieve densification. Glasses are produced through melting and quenching, while cements harden via hydration reactions. Applications span wear-resistant surfaces. Cutting tools, refractories, thermal barrier coatings, electrical insulators, and biomedical implants. Inspection focuses on porosity, microcracks, incomplete densification, and thermal shock damage, as these defects significantly affect reliability. Engineers must design components to minimize tensile stresses and stress concentrations, often employing compressive loading strategies to mitigate brittle failure. Ceramics offer remarkable advantages, including hardness, wear resistance, chemical inertness, and the ability to withstand extreme temperatures. These properties make them indispensable in applications such as refractories, glass linings, and thermal barrier coatings. However, their brittleness and sensitivity to flaws pose significant challenges. Crack initiation and propagation can occur suddenly, leading to catastrophic failure. Toughening strategies include incorporating fiber or particulate reinforcements, utilizing phase transformation mechanisms, such as zirconia toughening, and refining microstructure to reduce flaw size. Design considerations involve avoiding sharp stress concentrators, ensuring uniform densification during processing, and applying compressive stresses where possible. Quality assurance relies on defect control through advanced inspection techniques such as ultrasonic testing, acoustic emission monitoring, and thermal imaging to detect internal flaws before service deployment. Polymers are lightweight and corrosion-resistant, widely used in piping and coatings. Let's explore their structure and design considerations. Polymers are organic materials composed of long-chain molecules, and their properties are governed by chain mobility, degree of crystallinity, and cross-link density. They are classified into thermoplastics, which soften upon heating and can be reshaped, thermosets, which form irreversible cross-linked networks during curing, and elastomers, which exhibit rubber-like elasticity due to coiled molecular chains. Polymers are lightweight, corrosion-resistant, and easily processed into complex shapes, making them attractive for numerous applications. However, their mechanical behavior is time and temperature dependent due to viscoelasticity. The glass transition temperature, TG, marks the shift from rigid to rubbery states, influencing performance under varying conditions. Processing methods such as extrusion, injection molding, and compression molding determine molecular orientation and residual stresses, while curing schedules for thermosets are critical for achieving desired properties. Inspection focuses on detecting voids, weld lines, incomplete cure, and environmental stress cracking, which can compromise long-term reliability. Polymers provide significant advantages, including low weight, corrosion resistance, electrical insulation, and cost-effective manufacturing of complex geometries. These benefits make them suitable for piping, liners, housings, seals, coatings, and even 3D printed components. However, engineers must account for limitations such as creep under sustained loads, susceptibility to UV and chemical degradation, and thermal constraints relative to TG. Design strategies include reinforcing polymers with fillers or fibers to enhance stiffness and strength, selecting appropriate grades for thermal stability, and incorporating additives for UV protection and flame retardants. Environmental factors like humidity and chemical exposure must be considered to prevent premature failure. Inspection techniques may involve hardness testing, differential scanning calorimetry for cure verification, and visual or ultrasonic methods to detect defects and degradation. Composites combine matrix and reinforcement phases for tailored properties. We'll look at their architecture and mechanics. Composites are engineered materials combining a matrix phase, metal, ceramic, or polymer, with reinforcements such as particles, fibers, or layers to achieve tailored properties. The primary goal is to optimize stiffness, strength, and weight while improving damage tolerance and thermal stability. Common architectures include particle-reinforced, fiber-reinforced, and laminar composites, each offering unique performance characteristics. Fiber-reinforced polymer composites dominate aerospace and automotive sectors due to their high strength-to-weight ratios. Key variables influencing composite performance include fiber volume fraction, orientation, interface quality, and defect content such as voids and delamination. Processing methods like layup, filament winding, pultrusion, and resin transfer molding control these parameters, while curing and consolidation ensure structural integrity. Inspection focuses on detecting defects such as fiber misalignment, voids, and poor adhesion, often using ultrasonic or thermographic techniques. The mechanical performance of composites relies on effective load transfer from the matrix to the reinforcing fibers through the interface. Fiber alignment maximizes axial properties, while the matrix provides shape, environmental protection, and shear transfer. The rule of mixtures conceptually predicts axial stiffness and strength based on fiber volume fraction and properties, but transverse and shear behaviors depend heavily on matrix and interface characteristics. Failure modes in composites include fiber breakage, matrix cracking, debonding, and delamination, often occurring progressively rather than catastrophically. Design strategies involve selecting layup sequences to accommodate multi-axial loads and ensuring high-quality curing to minimize voids and defects. Inspection and maintenance require advanced non-destructive evaluation techniques to monitor damage evolution throughout service life, emphasizing the importance of quality control during manufacturing.